Hello, everyone. My name is Bo Jianhou. I'm currently a postdoctoral fellow at the University of Pennsylvania. This is a teaching demo for the interview from University of Washington, Tacoma. In this teaching demo, I'm very excited to introduce the attention mechanism in Transformer. By the end of this lesson, students will be able to understand the concept of representation learning, explain the concept of attention, and why it's useful in sequence processing. Identify the three key components in attention, which are query, key, and value. Calculate attention scores using a simple example with 2 to 3 words. Describe how attention allows each word to gather information from other relevant words in the sequence. Attention is firstly introduced in this paper titled Attention is All You Need. It is published in NeurIPS 2017. Just 8 years past, its citation has increased to over 152,000. I would say our large language models era is derived from here. This paper provides the core technique for ChatGPT, Cloud, DeepSeek, or any large language models. So I am very excited to introduce the core idea of this work to you. The model introduced in this paper is called Transformer. It is not this one, but this one. As you can see, it is a very complex model, and in today's course, I won't introduce all the techniques. I will mainly introduce the attention mechanism, which is one of the most important technique in this paper. Before I go into details, I need to introduce some background about machine learning and representation learning, since this idea will be adopted in the attention mechanism. In a particular supervised learning scenario, we first have a data set, and each sample here is a watermelon. Each watermelon is described by three features: color, root, and sound. The last column is the label indicating whether the watermelon is ripe or not. Given this dataset, we can use machine learning algorithms such as support vector machine, neural network, decision tree, logistic regression, etc. to train a model F. Then, given a new watermelon whose color is black, root is straight, and sound is dull, the model F classifies it as ripe. In machine learning, a model is essentially a mapping from instance X to label Y. Here, the three-dimensional vector is a representation of a watermelon. Traditional machine learning algorithms can work very well as long as we have good representations. But what if we don't have such clear features? In reality, the input instance could be an image, a sequence of words, a piece of music, etc. How to represent them if we want to apply the machine learning methods on them to train a model to classify them? The answer is we need representation learning. Representation learning aims to embed or encode the input instance into a representative vector. We call it embedding. That can capture the input's essential information. Representation learning is usually implemented by deep learning models such as convolutional neural network, CNN, recurrent neural network, RNN, or transformer. Here is a concrete example. Given two images of a dog and a cat, the representation model or encoder will encode the images into representation vectors or embeddings. With good embeddings, a classifier can easily classify them into cat and dog. The representation model and classifier are often merged into one model, which is called end-to-end model. Attention mechanism in Transformer is exactly a way of representation learning which aims to learn a good representation for each word in the sequence for the purpose of subsequent tasks such as task classification or task generation. Transformer is proposed for processing natural languages. Common applications of transformers include translations and question answerings. In this example, the input is a sequence of French words and the output is a sequence of English words. If we zoom in, we can see that there are a stack of encoders to encode the input into embeddings and a stack of decoders to decode the embeddings into the output. Let's continue zooming in to a pair of encoder and decoder. You can see that attention appears in every block, and it is one of the most important mechanisms in transformer. In self-attention, each word only attends to other words within the same sequence. In encoder-decoder attention or cross-attention, words from one sequence attend to words from a different sequence. Self-attention and cross-attention share basically the same mechanism. In today's talk, I merely introduce self-attention. You can learn by yourself how the encoder-decoder attention or cross-attention works. Self-attention functions as a representation module to update each word's representation vector to capture all useful information from other words. From this encoder block, this self-attention is used for updating the word embedding x1, x2, x3 in a sequence or a sentence to get their better representations z1, z2, and z3. Each new representation or embedding z1, z2, z3 integrates the information or attention from all the other words. Here is an example of the attention result provided by transformer. The sequence is the animal didn't cross the street because it was too tired. What does it in this sentence refer to? According to the figure, we can see that it has the most attention to the animal. You may notice in this example, some words are split into smaller units. These smaller units are called token. In natural language processing, a token is the basic unit of input the model's process rather than the word. Using token can significantly reduce the vocabulary size, handling unknown words, handling mixed language text, etc. But we use word instead of token in this talk for easy understanding. In self-attention, the goal is to update each word's embedding by capturing the information from other words. The general idea is, suppose there are three words x1, x2, x3 in a sentence, we calculate three pairwise similarities, or inner production, between the word that we want to update, which is x1 here, and all the three words in the sentence, including itself. We firstly calculate the similarity between x1 and itself to get E11. We then calculate the similarity between x1 and x2 to get E12. We finally calculate the similarity between x1 and x3 to get E13. Then we regard the similarities as the weight's attention to do weighted summation over all the words embeddings to get the new embedding, x1 new. Note that the weight E11, E12, E13 needs to be normalized by softmax before use to guarantee their summation is 1. In practice, to improve model's capacity or flexibility, we don't directly use the original embedding to calculate the similarity or attention. Instead, we create three additional vectors, query, key, and value for each word as surrogate embeddings via projection with three matrices WQ, WK, and WV. Query means what am I looking for? Key means what do I have to offer? And value means what information do I provide? Then we calculate the similarity between the query of the word that we want to update, such as Q1, and the keys of all the words, such as K1, K2, and K3 in the sequence. We then calculate the weighted summation over the values of all the words, such as V1, V2, V3 in the sequence. Note that we need to do softmax over all E before use. Let's go over all the process again. The figure on the left-hand side is a complete illustration for self-attention calculation for the first word. X1, X2, and X3 are three words as input. H1, H2, and H3 are their embeddings. For the teeth word, based on its embedding HT, we use parameters WK, WQ, WV to conduct multiplication with HT to generate key, query, and value separately. For the first word, its query Q1 will be multiplied by all the three keys to get the similarity E1I. And then Use softmax to normalize the similarity to obtain the first word's attention to the teeth word. Final embeddings for the first word A1 is the weighted combination of all the values V1, V2, and V3. Now we use a concrete example to show how to calculate the attention score and how to get the final embedding Z step by step. Given the initial embeddings x1 and x2, the task is to update the embedding x1, x2 to z1, z2 using self-attention. The method is firstly to create queries, keys, and values for these two embeddings by utilizing these three parameterized matrices WQ, WK, and WV. Given the embedding and QKV of the two words, we start to calculate the attention score of the first word to all the two words in this sequence. We firstly use Q1 to time K1 to get the similarity score between the first word and itself. Then we use Q1 to time K2 to get the similarity score between the first word and the second word. After we get the similarity scores, we divide them by 8, which is the square root of the dimension of query and key. This operation is used for better gradient calculation in softmax function. You can figure out the reason by yourself. Then we use softmax to normalize the similarity scores to get the weight. The final Z1 is the weighted summation over V1 and V2. The light color of V2 indicates its weight is small. Then we get the final Z1. To speed up the calculation, we can put the words in a batch and perform matrix multiplication operations in parallel. For example, we can get Q, K, V of all the words at all once, and obtain the new embedding Z of all the words at the same time. Here is the corresponding equation from the paper. It often appears in many technical articles or presentations. I hope you can totally understand this equation after today's talk. Finally, here is the take-home message. Self-attention is powerful for sequence processing. It can directly connect any two positions in a sequence. For example, in this sentence, the trophy didn't fit in the brown suitcase because it was too large. Attention helps connect it with trophy, regardless of the distance. It can also do parallel processing. Self-attention processes all words simultaneously. This enables much faster training and inference on modern hardware. Finally, self-attention can do adaptive focus. Attention weights show which parts of the input are relevant for each word. This creates an interpretable model where we can see what the model is focusing on. For example, when processing the cat sat on the mat, for the word sat, attention might focus heavily on cat. I hope this talk can let you fully understand the attention mechanism. Let me know if you have any questions. Thank you.